In the early morning hours of June 30, 1908, the sky over central Siberia tore open. A blinding flash of light was followed by a shockwave that registered on seismographs across Europe. The blast leveled an estimated 80 million trees across 2,000 square kilometers of the taiga. The timber was stripped of its branches and pushed outward in massive parallel rows away from a central epicenter. To understand the sheer scale of this destruction, we can look at the atomic bomb dropped on Hiroshima. That weapon released a blast yield of roughly 15 kilotons, collapsing the cityscape and leaving a permanent scar in human history. This visual compares that 15 kiloton baseline against modern computer models of Tunguska, which placed the 1908 energy release between 10 and 15 megatons. The Siberian blast unleashed at least 1,000 times the destructive energy of the Hiroshima bomb. Yet, when scientific expeditions finally reached the remote epicenter decades later, they found a baffling geographical void. There was no impact crater anywhere to be seen. The object never touched the ground. Solving how a cosmic body unleashes a multi-megaton blast without leaving a scratch on the Earth requires discarding our assumptions about solid iron rocks and looking closely at the volatile, extreme physics of a massive ice asteroid striking the atmosphere. When an asteroid-sized chunk of ice hits the upper atmosphere, about 100 kilometers up, it is traveling at hypersonic speeds, typically between 11 and 30 kilometers per second. It is widely assumed that friction causes the intense heat of a falling meteor, but the real culprit is compression. Moving vastly faster than the speed of sound, the asteroid violently crushes the air molecules in front of it, forming a bow shock wave that spikes localized gas temperatures anywhere from 5,000 to 15,000 degrees Celsius. Under that blistering heat, the front of the volatile ice doesn't even have time to melt. It instantly sublimates, turning directly from a solid into a gas, rapidly stripping away the asteroid's mass in a process called ablation. As the block of ice descends further into the denser layers of the lower atmosphere, the surrounding air begins to act as an astronomical brake pad, pushing back against the object with immense force. This formula shows the drag equation, the mathematical rule governing that atmospheric resistance. The force pushing against the falling asteroid depends heavily on two critical variables: the increasing atmospheric density, denoted by ρ, and the velocity of the object, squared. Because this drag force is proportional to the square of that extreme hypersonic velocity, the pressure applied to the front face of the ice asteroid grows exponentially. It experiences immense stagnation pressure on its nose, while its back face remains at near vacuum pressure. This severe differential creates a structural trap, subjecting the asteroid to a brutal combination of thermal stress and aerodynamic forces that far exceed the physical limits of solid ice. Unlike traditional silicate rock or dense nickel-iron meteorites, ice has remarkably low compressive and tensile strength. It simply cannot hold itself together under extreme physical stress. As the stagnation pressure on the nose exceeds the internal mechanical strength of the ice, the asteroid begins to violently deform and flatten. Scientists refer to this structural collapse as the pancake effect. This diagram shows the drag equation again, revealing how this flattened shape drastically increases the asteroid's cross-sectional area, represented by the variable A. This triggers a runaway mathematical feedback loop. A larger surface area directly guarantees a massive increase in atmospheric drag, which immediately causes further flattening, exposing even more surface area to the crushing air. Within milliseconds, the solid body entirely succumbs to the pressure, shattering into a cascading chaotic cloud of smaller ice fragments that are all still moving at hypersonic speeds. Stripping away the single solid form allows the entire kinetic energy of the fragmented cloud to instantly convert into thermal and mechanical energy, creating a violent high-pressure detonation wave. This rapid release of superheated gas and vaporized water, a catastrophic mid-air detonation known as an airburst, rushed towards the surface, flattening the Siberian taiga in 1908 and perfectly explaining the paradox of the missing crater. Understanding this physics dictates how we handle incoming threats. The famous Hollywood strategy of flying astronauts into space drilling into a hazardous asteroid and detonating a nuclear weapon from the inside is widely considered a catastrophic scientific error. Detonating a massive explosive deep inside a celestial body triggers a shotgun effect. Instead of vaporizing the threat, it shatters the asteroid into thousands of radioactive fragments that maintain forward momentum on the exact same Earth-bound trajectory. Instead of a single localized impact, the Earth's atmosphere would be completely overloaded. Those fractured chunks would trigger widespread, simultaneous Tunguska-style airbursts across entire hemispheres. The threat of a multi-impact bombardment leads planetary defense agencies to emphasize one ultimate rule: deflection over disruption. You never want to break the asteroid apart. If a nuclear weapon is absolutely necessary, scientists plan for a standoff detonation. By exploding a warhead a few hundred meters from the rock's surface, the intense burst of X-rays instantly vaporizes a thin outer layer of the asteroid. That physical blow-off acts like a giant rocket thruster, creating an equal and opposite reaction that gently nudges the intact object safely off course. Non-nuclear, kinetic deflection is already a proven reality. In 2022, NASA's DART mission successfully rammed a spacecraft into the Dimorphos asteroid, transferring enough kinetic energy to manually alter its orbital period while keeping the rock in one piece. The volatile power of an atmospheric airburst demonstrates why our survival relies on early detection and a calculated, gentle nudge, ensuring a planetary-scale detonation never has the chance to begin.